Hello, I've got an ammeter. Well, it's a voltmeter, ammeter, wattmeter. Let's take a look. It's that. In fact, I've got a few of these things. Here are three, but let's get one out of its bag. So this is a 100 volt, 10 amp voltmeter, ammeter, but it also displays watts because it calculates it from those. Oh, hello. That's an interesting shunt. Well, interesting for 10 amps anyway. Having said that, this power supply I bought recently has that shunt, which is even longer than this shunt. And this has a maximum output of 4 amps. So yeah, I guess that could be 10 amps. Let's power this up. I've got a 2-pin JST. That's actually a 3-pin. It is pos to the top and then neg, so yeah, I can use that. Pos to the top. I've had to cut off the little barb, but pos to the top and then neg. And the ammeter looks like this, so volts, amps, and calculated watts. There are two adjusters here, one for amps calibration and one for volts calibration. Okay, let's see if it's set up correctly. And I can do that with a power supply, my Ryobi ammeter. I've put some banana plugs onto the lead that came with this. So that plugs in there. So if I go into the Ryobi first, come out of that and go into this ammeter, and then go all the way back to the power supply, like so, we can compare these two ammeters. So I've got 1 amp, 5 volts. It won't get to 5 volts, of course, because this is effectively a dead short. It's just driving the two ammeters. So it's really just 1 amp. Let's have a look at that. And that's the voltage. So yeah, we've got 1 amp here, 1 amp here, and HHH. What's one of them? Well, apparently that means overload. So overload at 10 amps. Let's bring the current down a bit. Oh, so there we are, 978, 980. And this actually says 9.8 amps. So it's reading 10 times higher than it should be. This is a 10 amp ammeter and it's reading 9.8 amps when only 0.98 amps is going through it. So yeah, there's something majorly wrong with this ammeter. And in fact, if you go to the seller's sale page, you've got this review. Don't buy. Unit does not work as advertised. The ammeter displays a value that is 10 times too high. When the actual current is 0.5 amps, the meter displays 5 amps. Both units that I've received have the same fault, so I expect this to be a production fault. The meter is totally useless. And yeah, as it stands, the meter is totally useless because when you get a volts reading here, I haven't got the plug connected for that, you would have the watts measurement would be all wrong. That would be 10 times too high as well. So there's an adjustment potentiometer here. Can we adjust it? So 9, we want 0.978. Let's take it down. That's gone HHH. Oh, clockwise goes down, and the lowest we can go is 7.7 amps. So no, the adjustment doesn't work either. It was nice and accurate, wasn't it? 978. Oh, I've gone a bit too far. But 978, just 10 times wrong. Now I've got to come clean and say that the beginning of this video was all faked. I've been dealing with this problem for some time. I contacted the seller, and in fact they didn't respond, and AliExpress jumped in and just said, okay, we have a solution for you. Send the items back to China for a full refund. They did say that the seller would pay postage, but I'd rather spend my time, rather than packing all this stuff up, sticking labels on and going to the post office, I'd rather think about how I can fix this myself. And this was my first attempt. So I wrapped tinned copper wire around the bottom part of the shunt in the hope that I could have a little bit of shunt remaining. It didn't really work because it still measured 2 amps when there was 1 amp going through it. So I had to sort of solder out one end of the remaining shunt. And I didn't know until I looked it up what this metal is. And it's not copper. It's something called manganese. And manganese has the property, a bit like constantan, has the property that it has a very low temperature coefficient. And so for a measuring device, you don't really want it to be susceptible to changes in temperature affecting the reading that you're getting. So it has an extraordinarily low temperature coefficient. It's barely affected by temperature at all. And of course, by putting in copper across here, I've now got the temperature coefficient of copper as well. And that's nowhere near as good. So if we look here on the Wikipedia page for electrical resistivity and conductivity, we can see that the temperature coefficient for copper is 4 times 10 to the minus 3. Now I presume it's resistivity per degree Kelvin. I presume that's what it is. So the resistivity changes by a factor of 4 times 10 to the minus 3, so 0.004 for every degree Kelvin or degree centigrade that the temperature changes. If we go down to manganese, which is here, it's 0.002 times 10 to the minus 3. And that's why manganese exists, because it is very unsusceptible to changes in temperature. It does have a higher resistance than copper, 48 times 10 to the minus 8, whatever these are, ohms times meters, whereas copper is 1.68. So manganese was, what was it, 48. So it's got a lot more resistance than copper, so I was right to put the copper across it, but of course it's got this problem with temperature coefficient. And so putting this copper across the shunt to try and short most of it out isn't really the solution. Although, having said that, of course, there's copper traces running up to these pins. So there is copper in the circuit, and there are copper wires, of course. These high current wires are all copper. But anyway, this was a mess and didn't really work. So we'll put that to one side. This ended up being the solution. So I just simply, let's get the focus back. I just simply cut the top off the manganese wire shunt and soldered it right down flat against the, well, as flat as I could get it, against the PCB, really just to get it as short as possible. And that ended up with something like, it measured 3 amps for the 1 amp that I was putting through the circuit. So it needed more than that. So shall we modify this one that's currently reading 10 times too high, cut this shunt down, and see what we end up with as an amps reading. Okay, let's unhook all this, turn the power supply off, unhook the ammeter from this, clear my desk, and then let's cut this shunt down. So let's cut the top off this manganese shunt, leaving a little bit of return so that I can solder it back into the PCB. That should be enough. Right, I'll use that bit and solder that into the PCB. So the first thing I've got to do is get these 2 stems out. Right, iron on hot on 360, that should do it. Oh, tip's a bit mucky, but let's give it a go. Okay, grab that with the pliers, heat that up. Can I impart enough heat into this to get it? Yes, I can. Let's take the other one out. I'll just press the back button on this soldering iron. Okay, let's get some heat on the other one. It's getting the heat into it that's the problem. Let's go to 400 degrees by pressing the boost button. It's getting a good physical connection between the iron and the hole. Okay, so those are out. Let's suck these out with the solder sucker. Okay, solder sucker, in you go. Let's hope, oh, where's my bucket of lead? Just a bit of solder on the tip, because the tip shape and the hole shape are not a good match, and therefore it's difficult to impart enough heat unless you've got a little bit of solder on there. Okay, let's get that hole sucked out and see if the manganese shunt will fit in those holes. So lower it down, and I haven't had to remove yet the PCB from the plastic housing, but have I sucked these out well enough to, oh yes, that has gone in. Yeah, that's fine. So I want to get it as low down as I can. That I think looks okay. Let's solder it in. Use the iron on the hot setting again, 360. Get that to flow all around, which I think it has. I really need to turn this round to do the other side. I'm not sure what you'll get to see, but I need to get to see this as well as I can. It's just not flowing around that side. Okay, that's got it. Right, so that's the manganese as short as we can get it without sort of moving the hole across a bit. Right, let's see what that gives us. Turn on the power supply. So that's 1 amp. Yeah, so like I say, that's now reading 2.5 amps. Oh, it's a little bit better than I thought. So that's down to about just slightly over a quarter, and of course I can adjust that away. So I think it was positive, wasn't it, clockwise, to bring that down. So yeah, I can get that down to 2.5 amps. In fact, I can take it all the way down to 2 amps with this pot, but it'd be quite nice to have this pot roughly central. So I need to do a little bit more to bring that from 2.5 amps down to the 1 amp that I'm measuring both on my ammeter here and also here 1 amp on the power supply. So what else can I do to this thing to get the amp reading down? Well, the circuit here for reading the voltage across the ammeter shunt is top of ammeter shunt goes into this potentiometer. Wiper of the potentiometer runs round here through that, I can't read it, resistor, and then it looks like it goes straight into the microcontroller, or this might be a dedicated voltmeter, ammeter, wattmeter chip. And then the bottom of the pot goes through this. Now actually this resistor is a 01B, which from memory is a 1K, and this is a 01C, which I think is 10K, and then 01D is 100K, as I remember it. I will check that. So what we appear to have is this pot. Now I need to take this out to have a look at the value of the pot. So 4 screws holding the PCB to the front panel. Let's take those out and take a look at this thing when I get the screws out. So here are the 2 potentiometers. The A adjust is this one that's connected up to the shunt. So we'll have a look at the A adjust value, and it's a 502, so that's a 5K. The voltage adjust pot is actually also a 502. Camera's having a job because it keeps seeing all this lot. So they're both 5K resistors. So the circuit here is top of ammeter has a small voltage on it. That goes first through a 5K resistor and then a 10K resistor down to ground. This area here looks like ground plane. So what we want to do is reduce the value of that 10K resistor to bring the whole voltage measured at the top end of the shunt down. I mean, we could reduce that resistor and increase the value of the pot, but let's just leave the pot in. Yeah, I mean, I don't have any of that kind of pot of different values. And I think, and I have of course already done this on other ammeters, that the easiest way to modify this resistor is just to melt it off the board and blob the solder across the pads. So here we go, let's do that. Get some solder on the iron to get that resistor hot. Heat both ends, lift it off, so that's it off. And now I'm just going to flood those two pads with solder. And there it is, blobbed across. So now we've got the 5K pot with its bottom end tied hard to ground. Let's see what we get. So we've got this annoying 20 milliamp offset. Now, were we getting that when I first powered this up? I think we were, although I think it might have been 10 milliamps then. But anyway, let's get this hooked up to the current path. So, oh, that's all still on actually. Okay, let me just reposition the camera. And yeah, so I've got 1.12 amps here, 1.001 amps there, 1.002 amps down here on the power supply. So what I want to do now is trim this so it'll be clockwise. Oh, that's gone slightly too far. Now, of course, it's much more sensitive now because we're using the 5K to span the full range of trimming. So that's one thing we've lost. We've lost the sort of soft sensitivity of this calibration pot, and now it's all rather harsh. But there it is, 1.01 amps, which it's supposed to be 1.00, isn't it? But I'm not sure whether I'm going to be able to. I want the tiniest smidge of a movement on there. Yeah, so it is more difficult to move this pot and get it calibrated now. But there we are, 1.01 or 1.00 amps. The next thing to do, I'll tidy the desk a bit, we'll check for linearity. So we'll raise it up through the amp range and see if this responds linearly. So 1 amp on all the devices. Okay, let's raise that up to about 2 amps, 2.030. I'm going to have to, because this thing moves so fast, you can't control it other than individual button presses. Okay, so 2.001, 2.000, and this is now saying 1.99. I suppose I could peel this off, couldn't I? Because it's not easy to read. Or I could bring the blinds down. Perhaps I'll do that as well. So that's not bad, but it's a little bit out. Okay, let's try 3 amps. 3.06. So 3.06, 3.06. And this is reading 3.04. So where's my adjuster? Let's adjust that to 3.06. Oh, it's very sensitive. 3.07. Okay, let's go up to 4 amps. A little bit further than that. 4.09. Yes, as you can see, it's just so difficult to get that exactly right. So you end up pressing this button furiously. Okay, 4 amps. Oh, that's pretty good. 4 amps there. 4 amps on my Ryobi DMM and 4 amps on this thing. So now I've brought it all the way down to half an amp, 0.5, 0.499, but this says 0.53. So yes, the linearity has suffered a bit. And in fact, if we turn that off, 0 amps, that's showing volts at the moment. So 0 amps, 0 amps. And this has got this offset of 20 milliamps, 0.02. So it hasn't really fixed it very accurately, but at least it's now kind of working. And if you're going to use this in a non-critically important and you don't need precise accuracy application, then it might be good enough. Now, of course, there's another problem, and that is that having this shunt, which I think was 2.5 times the resistance that it really should be. So we've had to bodge the measurement with this removal of that resistor there. We've got a higher burden voltage than is really necessary here. If we had the proper shunt, a different piece of manganese, shorter perhaps, or certainly thicker diameter, then we would have a lower burden voltage. So yeah, we've also got this additional problem that we've got a higher than necessary burden voltage. Now I've got 7 of these meters in total. I bought 3 initially from one seller. That's the seller where the previous purchaser wrote, don't buy this meter because it shows 10 amps when it's only 1 amps. Then I thought, okay, I'll buy 4 more from another seller, but those are these new ones that I've opened today. And of course they also have the piece of manganese, which I think really is a 1 amp shunt, but software in the unit which makes it measure 10 amps for 1 amp going through it. So at the moment there does seem to be a large number of these, and they may be with most of the sellers, you just don't know. So this is really your only option, is to take these ammeters that say 10 amps here, but they actually measure only up to 1 amp because, well, something in the electronics, the shunt doesn't match the software. Something's wrong. It is fixable. It's not 100% accurate, and you do have that burden voltage problem, but it does kind of fix it. So maybe that's good enough. Cheerio.